Good day, Dr. Ryan. I am Vincent from BSCPE 41 and this is my final examination for Computer Architecture and Organization. I'm going to tackle 4 topics: how CPU works, evolution of CPU, SAP1 operations, and SAP1 programming. Let's start on how CPU works. The Central Processing Unit or CPU, often referred to as the brain of a computer. It executes instruction through the intricate fetch, decode, execute cycle. In the fetch stage, the program counter guides the CPU to the next instruction's memory address, prompting the retrieval of the instruction from the memory. This instruction is then loaded into the instruction register, setting the stage for the decode process. From here, the control unit unravels the instruction, identifying the opcode and determining the operation to be performed, along with the associated operands. Moving to the execute stage, the CPU carries out the specific operation using the arithmetic logic unit or ALU and potentially accessing memory through the memory address register and memory data register. If the instruction produces a result that needs storage, the write back stage ensures that data find its designated register or memory location. The program counter is subsequently updated to indicate the next instruction, those initially the cyclic process anew. Throughout these stages, various registers such as accumulator, index registers, and data registers act as temporary storage units, facilitating the swift exchange of data during the execution of instructions. The CPU's internal clock governs the timing of these operations, dictating the pace at which instructions are processed. Additionally, cache memory enhances efficiency by storing frequently accessed instructions and data for rapid retrieval. To further optimize processing, some CPUs employ techniques like pipelining. It allows multiple stages of the fetch, decode, and execute cycle to overlap. In more advanced systems, multi-core processing is leveraged, enabling the CPU to execute multiple instructions simultaneously by utilizing multiple processing cores. In essence, this orchestrated interplay of registers, the arithmetic logic unit, memory access, and control unit, coupled with clock synchronization and memory optimization strategies, empowers the CPU to fulfill its role as the computational powerhouse of a computer. The efficiency and agility exhibited by the CPUs significantly contribute to the overall speed, responsiveness, and capabilities of a computer system, allowing it to execute diverse tasks and run complex applications with finesse. Now, let's use layman's analogy for better understanding on how CPU works. Imagine a CPU or central processing unit as the brain of a computer. Just like your brain processes information to make decisions and control your body, the CPU processes information to run programs and operate your computer. Now, think of the CPU as the chef in a kitchen. The chef itself is the CPU, which receives order, which is the instructions, from the waiter, which is the software, and then goes to work. The kitchen tools and ingredients serves as the registers, cache, and memory are used to prepare food and cook the dish, which is the perform calculations and executed task. The chef follows a recipe or the program step by step, performing calculations and manipulating data as needed. The faster the chef works, the quicker the dish is ready. Similarly, the speed of a CPU is often measured in gigahertz, indicating how many instructions it can execute per second. Just like a skilled chef can handle multiple orders simultaneously, modern CPUs often have multiple cores, allowing them to work on several tasks at the same time. This is like having multiple chefs in the kitchen to prepare different dishes simultaneously. In summary, the CPU is like the chef in the kitchen, following recipes or program to process information and produce the desired output of your computer. Next is the evolution of the CPU. During the mid-1960s, a miniaturization revolution kick-started the integrated circuit, paving the way for a paradigm shift in modern society. In March 1971, Intel launches the 4004 CPU, a groundbreaking semiconductor product with 2,300 transistors, marking the beginning of a new era in integrated electronics. The Intel 4004 was capable of executing 46,250 to 92,500 instructions per second, a significant leap from the first electronic computer, ENIAC, built just 25 years earlier. What made the 4004 revolutionary was not just its processing power, but also its energy efficiency, compact size, and affordability, setting the stage for further advancement. Fast forward to September 2017, with the launch of the Intel Core i9 7980XE, capable of performing over 80 billion instructions per second, showcasing a 900,000 times increase in processing power. The CPU's ability to process data is based on binary representation, with bits representing two possible states. The CPU operates on data in chunks known as words, with word size forming the core of its architecture. The original Intel 4004 had a 4-bit word, while modern CPUs typically operate on 64-bit or 32-bit words. Instructions are fundamental operations in executing by the CPU. Instructions are fundamental operations executed by the CPU, forming the basis of all computer programs. CPUs operate through a three-step process: fetch, decode, and execute. The fetch phase involves loading instructions from external memory into the CPU, often DRAM. Addressing accomplished through data and address buses allows the CPU to access specific locations in memory. The decode phase involves breaking down an instruction into opcoded operand, representing a specific function and accompanying data. The execution phase triggers the configured CPU to perform the operation, often involving the arithmetic logic unit, which handles basic arithmetic and logical operations. The CPU's operation is synchronized by a clock, with clock rates measured in hertz. As CPU advanced, clock rates increased, but optimizing the use of clock cycles became crucial for efficiency. However, the pursuit of higher clock rates faces challenges, including unpredictable results, power dissipations, and heat buildup. The second part of our discussion is on how CPU stores data, discussing the binary representation of information and the concept of bits, bytes, and words. It explores the mechanic of basic CPU operation, introducing the classic reduced instruction set computer or RISC pipeline and the fetch phase, where instructions are loaded into the CPU. And we will explain how data moves between the CPU and RAM through a data bus and address bus, detailing the role of registers and the program counter. The evolution continues with the introduction of the Intel 8008 in 1972, featuring 8-bit architecture, 14 bits of address capacity, and indirect addressing capabilities. It also touches on interrupts, a mechanism allowing hardware signals and events to post-program execution. The Intel 8080 introduced in 1974 marked a significant milestone with 16-bit address capacity and an external bus controller for improved interfacing with RAM and the system components. The series then explores the transition to the Intel 8086 and 1978, a fully 16-bit CPU with improved memory management, a segmented memory structure, and support for higher-level program languages. The complexity of the 8086 contributed to the Intel's commitment to complex instruction set computer architecture. Now, let's move between the difference between CISC and Reduced Instruction Set Computer or RISC architectures, emphasizing the advantage of AISC in supporting robust instruction set. The Intel 8086 performance was enhanced through techniques like prefetching and the introduction of the 8087 floating point coprocessor for efficient floating point math operations. The success of the 8086 is intertwined with the IBM's personal computer, launched in 1981, powered by a variant of the 8086, the 8088. The IBM's PC's success, coupled with Microsoft's development of PC-DOS, solidifies the 8086 legacy as the standard for personal computing, paving the way for the prevalence of PC architecture in today's computer. In 1981, Microsoft hired former Xerox programmer Charles Simonyi to create a new word processor, leading to the development of Microsoft Word. Initially released in 1983 on MS-DOS, Microsoft Word was unique as one of the few DOS programs designed for use with a mouse. Over the years, it evolved into a featured pack application, contrasting with its humble 150 kilobyte size in the first version. The 1980s and 90s saw a rapid expansion of software complexity, driving demand for 32-bit processors. Early 32-bit architectures faced challenges, with the 68020 being one of the first successful ones. In 1986, Intel introduced the 80386, a true 32-bit processor with enhanced memory management, debugging capabilities, and compatibility with previous generations. The 8086 architecture allowed direct addressing of 4.2 GB of memory, making it a significant advancement. Its sophisticated memory management unit enabled the development of modern operating systems by allowing programs to load anywhere into memory without constraint. The 386 utilized a three-stage pseudo-pipeline mechanism to enhance processor throughput. The concept of instruction pipelining, dividing the instruction into sequential stages for parallel processing, became pivotal for increasing processing efficiency. Pipelining faced challenges like data hazard, control hazard, and self-modifying code, prompting techniques like pipeline bubbling and operand forwarding. Memory access speeds lag behind processor speeds, leading to the introduction of caching. Caches held copies of data from system memory, mitigating the performance gap. Caching system evolves from simple to complex, with hierarchical structures and multi-megabyte size. Caching organization involves direct mapping, set associative caches, and replace policies like least recently used. Caches aims for high hit rate as cache misses incurred significant performance penalties. Cache coherence protocols manage synchronization between caches and multiprocessor systems. Write policies like write through and write back dealt with updating system memory, when writing to the cache. The integration of caching and pipelining in processor design during the 1990s played a crucial role in achieving higher processing efficiency. As processors became more complex, software optimization became essential for utilizing the instruction cycle optimally. Overall, the evolution of processors, software, and associated technologies during this period laid the groundwork for sophisticated computing systems as we use today. Next, let's move on to the SAP1 operations. The simplest possible one is a basic 8-bit microprocessor designed for educational purposes to help individuals understand the fundamental concept of computer architecture. Now let's explore the full operation of SAP1. The clock pulse. SAP1 operates on a clock mechanism and each operation is synchronized with the clock pulse. For the fetch cycle, the addresses of the instruction to be fetched is loaded into the memory address register. Next is the memory read operation. The control unit sends to the read from memory. The content of the addressed memory location is loaded into the memory buffer register. The memory of MBR is transferred to the instruction register. After the fetch, we have the decode and execute. The opcode decoding, the control unit decodes the op from the IR to determine the operation to be executed. When selecting the register, depending on the opcode, the control unit activates specific operation and registers such as accumulator, B register, input register, and output registers. The SAP1 ALU can perform basic arithmetic operations such as addition and subtraction. The accumulator and B register are the operands for ALU operations. The ALU produces the result and the result is stored back in the accumulator. As for the load and store operations, load accumulator, the content of the memory location is loaded into the accumulator. The store accumulator, the content of the accumulator is stored back into the memory location. As for the input and output operands, the input, the data from the external devices, can be loaded into the input register, while the output, the content of the accumulator, can be moved to the output register for display or further processing. As for the jump and control operations, jump, it alters the sequence of instructions by changing the program counter to jump to a specific memory address. The conditional jump, it's jump based on the certain conditions such as 0 or carry flags. As for the increment and decrement operations, the increment increases the content of a register by 1, while the decrement, it decreases the content of a register by 1. The halt operation, halt, it stops the processor, bringing it to a halt. The control unit generates control signals based on the opcode, directing the flow of data and operations. As for the clock reset, the SAP1 includes a clock reset mechanism to synchronize the operation and reset the system for subsequent cycle. The SAP1 architecture is intentionally simple, providing a clear and educational understanding of the fundamental operations within the microprocessor. It serves as a fundamental for more complex architectures and help learners grasp the concept of instruction cycle, data movement, and basic arithmetic logic operations in a computer system. Now, let's move to the last part of our discussion about the SAP1 programming. The following image is an example of SAP1 emulator. Now, let's explore. The SAP1 emulator is inspired by the chapter about as simple as possible architecture from Digital Computer Electronics 3rd edition by Albert P. Malvino and Gerald A. Brown. It has been designed as a visual learning tool for fun and experimentation. Entering the program instruction of SAP1 emulator, When a program is executed, the program counter will start at 0 and load the first instruction from the memory address as the program cycles RAM address 1, 2, and 3, and so on until the program reaches a halt or until reaching address 15, after which the program will wrap up around and continue to run from 0. LDA stands for load accumulator and will populate a value from memory into the accumulator known as reg A or register A. The instruction accepts a single hexadecimal input which corresponds to the memory address of the value to load. Add stands for add and it will take the value of the specified memory address and moves to the buffer registry known as reg B or register B. During program execution, the content of reg B will be summed with the contents of reg A and it will be indicated in the sum register. The value from sum will then be moved to reg A where it can be used later in the program. The instruction accepts a single hexadecimal input which corresponds to the memory address of the value to use. Sub stands for subtract and it will take the value at memory address and move it to the buffer registry known as reg B or register B. During program execution, the contents of reg B will be subtracted from the content of reg A and it will be indicated in the sum register. The value from the sum will be moved to the reg A where it can be used later in the program. Out stands for output. It will take the contents from reg A and display the numeric equivalent on the digital numeric readout in the decimal form. Halt stands for halt and will immediately stop the program when executed. It is important to use halt at the end of the program to ensure the execution does not run over into the set values in RAM, which will result in computer garbage. And that's all for SAP 1 programming. And that concludes my final examination for computer architecture and engineering. Thank you and have a nice day.